In Unit 3, we're going to be talking about atoms and elements. If you think about it, take a piece of aluminum foil and split it in half. Obviously, it's not the smallest piece possible. We can break it down further. But the question is, how far can I go? Is there ever a smallest piece of aluminum? Well, the answer is yes. It used to be way in history they didn't think so. They thought you could do it forever. But in fact, now physically we couldn't do it. But in theory, we could keep breaking it smaller and smaller until we get to the smallest piece of aluminum, which would be called an atom. So since aluminum is an element, and we're going to talk about the difference between elements and compounds a little bit more, but since aluminum is an element, the smallest particle is called an atom. And if you tried to break the atom any further, you would no longer have aluminum. So there is a smallest particle of an element that still retains the properties of that element, and that is called an atom. So the atomic theory, how did it come to be that we came up with the atom, and so we're going to talk a little bit about the history of it. But chemistry is founded on these 4 fundamental assumptions about atoms, and we call it the atomic theory. Of course, it's still a theory because we're not absolutely sure. However, it's pretty well ingrained. However, we do keep finding newer and newer things that maybe adjust our theory just slightly. But for our purposes, these things are going to make up the atomic theory. So first of all matter is made up of atoms. The atoms of any given element are different from the atoms of all other elements. Chemical compounds are made up of 2 or more atoms combined in specific ratios that don't change. And chemical reactions change only the way the atoms are combined in compounds. The atoms themselves are unchanged. All right, so first let's talk about the structure of an atom. You probably know a little bit about this. Atoms are made up of 3 subatomic particles: the protons, the neutrons, and the electrons. The protons and the neutrons are tightly bound inside the center of the atom, which we call the nucleus. And then the electrons are located outside the nucleus. It's thought that they move very rapidly around. Now the protons and neutrons are also moving, but they're held tightly together and they don't move outside of the center of the atom. The electrons can move all over the place. Now the nucleus is small but very heavy because most of the mass is located inside the nucleus. The protons and the neutrons are the particles that have most of the mass. Electrons are much, much smaller, so most of the atom is empty space surrounding the very tight, dense nucleus. So let's just review a little bit. Again, protons, neutrons, and electrons. Maybe not review, but introduce them and review them a little bit. Protons, like I said, are located in the nucleus of the atom. Protons carry a +1 electrical charge, and they have a mass of 1 atomic mass unit, or AMU. It will be the abbreviation for atomic mass unit. Neutrons are also located in the nucleus. They carry no electrical charge. They're neutral, so neutron, neutral. And they also have a mass of approximately 1 atomic mass unit. Now, what's an atomic mass unit? We'll talk about that in just a minute. Electrons, then, are located outside the nucleus of the atom. They carry a -1 electrical charge. They have a mass of 0.00054 atomic mass units, but we generally just say, oh, they have a 0. They have no mass. Of course, that's not totally true, but compared to the proton and neutron, they're much, much smaller. So we generally say they have 0 mass. And electrons move rapidly around the heavy nucleus. So here's just a chart to sort of talk about the same the same things that we just saw. A common symbol for the electron is E with a little negative charge attached to it. Again, the charge is -1. Now here's where AMU comes in. If you look at the mass of the proton and the neutron, now they're very, very small. So in fact, their mass in grams are 1.7 times 10 to the minus 24 grams. So that's really tiny. So what we do is we say, well, a proton and neutron are approximately the same size, so we're going to give that the unit of AMU, we're just going to call it 1 AMU. And then we compare the electron to the proton and neutron, and that's where the 0.00054 comes from. You can see 1.7 times 10 to the minus 24 grams is the weight of the proton, and the electron is nearly over 1,000 times smaller. So that's where that comes from. Now, you don't need to remember the mass in grams. You just need to remember the mass in AMU. You can see the proton uses the symbol P. Sometimes it uses the symbol H+. That'll make more sense later in the semester. Neutron is given the symbol N. Again, the neutron has 0 charge. The proton has +1 charge. The electron has a -1 charge. The mass of the electron is 0, the mass of the proton and neutron are 1, and then of course the electron is outside the nucleus and the other two are inside the nucleus. So this will be a handy chart to go back and review before you take the test. All right, so the atomic number of an atom is the number of protons that atom contains. And so when we say the number of protons an atom has, we call that the atomic number. The atomic number is given the symbol Z. So if we're looking at the periodic table, the atomic number is the number that is that's the whole number. Now, on different types of periodic tables, the number can be different places, but generally it's on the top. You may want to, we'll talk about periodic tables later, but it's the whole number. That is the atomic number, and it is the number of protons. All right, now the mass number of an atom is the number of the sum of the number of protons plus neutrons. Remember that the protons and the neutrons each have the mass. They have an AMU of 1. The electrons are 0. So the mass of an atom is determined by the total of the protons and the neutrons. The mass number is represented by the symbol A. Now, I have no idea why the atomic number is given Z and the mass number is given A, but that's how somebody back there decided it. So you'll just have to remember that. Now, the mass number will also be a whole number. It's somewhat related to the bottom number on the periodic table, and again, we'll talk about this much more later on. But for now, what I want you to remember is that the mass number is a whole number, and it is the total of the number of protons and neutrons. Okay, so let's look at this example. Fluorine, the number at the top, 9, means that it has 9 protons. Also means its atomic number is 9. So fluorine has 9 protons and its atomic number is 9. Now, if that fluorine atom has 10 neutrons, then what will the mass number be? Well, the mass number will be the total of the protons plus the neutrons, 9 plus 10, or 19. So we'll talk about how to write the symbols in just a second, but since we're talking about a particular fluorine atom that has 9 protons and 10 neutrons, we'll write it as fluorine-19. We write the name of the atom dash the mass number. Now you can see that that's actually the same number as the bottom number, but again, that's not always true. The bottom number is usually some decimal, and again, we'll talk about that later in this unit. So here's another way that we can represent an atom. It's called a nuclide symbol. What we do is we write the symbol of the element. Then to the left on the bottom, we write the atomic number, which is Z, or the number of protons. And then the top number to the left of the symbol will be the mass number, or which is equal to the total protons plus neutrons. So in the case of fluorine that we've just been talking about, F is the symbol for fluorine. Fluorine has 9 protons, so we put a 9 to the bottom left. Fluorine has 9 protons and 10 neutrons, so the total mass number is 19. So notice that the top number is protons plus neutrons. So if you need to find out how many neutrons an atom has, you can subtract the bottom from the top. Or if you know the number of neutrons, to find the mass number, you add them together. So fluorine has 9 protons, 10 neutrons, a mass number of 19, and the symbol of F. Now, we haven't talked much about electrons yet, and we're going to get much more into it in Unit 4. But, and also in Unit 5, we're going to talk about different things having to do with electrons. But for right now, keep in mind that a neutral atom means that the charges are balanced. Since protons are positive, electrons are negative. In order to be balanced, we have to have the same number. And so, is, at least in this unit so far, the number of electrons will always equal the number of protons. So this element, fluorine 19, has 9 protons, 10 neutrons, and 9 electrons. All right, so let's do some examples. What are 2 ways to represent the atom that has 28 protons and 32 neutrons? First of all, 28 protons. 28 protons is the atomic number. So to write the symbol, we're going to have to figure out what the element is. 28 protons, we look on the periodic table. 28 is nickel, Ni. So, the bottom number will be 28. That's the atomic number, or the number of protons. The symbol is Ni, and then the top number will be 60. Why is it 60? Because the number of protons is 28, the number of neutrons is 32, and the total is 60. So the symbol for nickel 60 is seen there, nickel with 28 on the bottom, 60 on the top. And again, it's got 28 protons, 32 neutrons. 60 minus 28 is 32. It also has 28 electrons because it has 28 protons. All right, second example. How many protons, neutrons, and electrons are in magnesium 26? Well, magnesium 26, again, the dash 26 is the mass number, so that's the total of the protons and the neutrons. Now, in order to find out what the number of protons are, we have to look up magnesium. Magnesium is element number 12, which means there are 12 protons. Since the mass number is 26, that's the protons plus the neutrons. If we subtract the 12 protons from 26, we have 14 neutrons. So magnesium 26 has 12 protons, 14 neutrons, and since electrons equal the protons in a neutral atom, there will be also 12 electrons. So before we go any further, you might want to, if you haven't done it already, you might want to make sure and print off a periodic table so that you can refer to it the rest of this lecture. There's a link to it in the content folder for Unit 1, but if you haven't gone to there, one of the really good ones is Web Elements, just as it's spelled, www.webelements.com. They've got a couple of different periodic tables that you can download. So anyway, so far we've talked about protons, neutrons, and electrons. And protons, you can see where that comes from. The number of protons is equal to the atomic number. So like on the last slide, magnesium had 12 protons. Its atomic number is 12. 12 identifies magnesium. So the number of protons is really important and really easy to see on the periodic table. However, neutrons can change a little bit. The number of neutrons can change. And so somehow you can't know that automatically. Somehow you have to be told how many neutrons there are, either directly by saying there's this many neutrons, or by looking at the mass number and subtracting the two to find out how many neutrons there are. So you can actually have two atoms that are the same element, which means they have the same number of protons. However, they have a different number of neutrons and therefore a different mass number. If you have two of these atoms, they are called isotopes. So an example is chlorine. Chlorine has two different isotopes. And this is something that's in nature. It's not something that you can know somewhere. You have to look it up. And so don't worry about where the number of neutrons is coming from. This is something that's been determined through nature. So it would have to be, again, told to you in some way. There are in nature two chlorine atoms, two types of chlorine atoms. Both of them, of course, because it's chlorine, have to have 17 protons, so that never changes. Isotopes have the same number of protons. However, we have one isotope of chlorine, which is chlorine 35, and that will have 18 neutrons. So 17 protons and 18 neutrons gives us the total mass number of 35. Chlorine 37 has 17 protons and 20 neutrons. And so remember, protons and neutrons have all the mass. And so that's why the mass number for chlorine 37 is heavier than the mass number for chlorine 35, because it has two extra neutrons. Now also you'll notice that because they have the same number of protons and it's a neutral atom, they also have the same number of electrons. So they have the same atomic number but different mass numbers. Because they have the same number of protons, they have the same number of electrons. So the thing that changes is the number of neutrons and also the mass, and these are called isotopes. All right, let's look at a few more examples. What is the atomic number for nitrogen? If you look on your periodic table, you'll see, we'll get the answers in. If you look at your periodic table, you'll see that the atomic number for nitrogen is 7. It has 7 protons. If the nitrogen atom I'm talking about also has 7 neutrons, what will the atomic mass number be? 7 plus 7 is 14, so it'll have a mass number of 14. How will we write this symbol? We'll write the symbol with N for nitrogen. 7 will be the bottom number for the number of protons, and the top number is the mass number, protons plus neutrons. All right, what element has 49 protons? Again, if you look over at the periodic table, you'll see that it's indium, In. If the mass number is 115, how many neutrons are there? Well, in this case, remember that the mass number, 115, is the protons plus the neutrons. So if we subtract the two, if we subtract 49 from 115, we get 66. That's how many neutrons there are. I didn't put it on here. What would the symbol be? The symbol would be In. 49 would be on the lower bottom. And 115, don't get confused, don't put the 66. 115 will be on top. Okay, what is the mass number of an atom with 22 protons and 26 neutrons? Well, the mass number, you add them together. So the mass number would be 48. Write the nuclide symbol for this. Okay, well, we don't know what element it is, but we know it's 22 protons, so we need to look at the periodic table. That's titanium. So titanium, we have, again, the 22 on the bottom for the number of protons, and now the 48 will be on top for the mass number. Now here's one. How many neutrons are in plutonium-244? Well, you might not know where to go with this, but remember, 244 is the mass number. Mass number is protons plus neutrons. They didn't tell us how many protons we have. But don't forget, you can look it up. Plutonium happens to be, and you might have a little problem. You'll have to look up the, if you're a little bit slow, you might have to look up the symbol for it. Plutonium is Pu, which is element 94, so there's 94 protons. So if we take 244 minus 94, that means we have 150 neutrons. Again, if we wanted to write this symbol, we would have Pu would be the symbol. The bottom number would be 94, and the top number would be 244, protons plus neutrons. Okay, I hope that helped you. You might want to practice a few more. If you, I don't know, you might find something online to, or go back and do the reading. Okay. So we've already talked about this a little bit. The atomic mass unit is a unit, so it's a unit, but it's not really meaningful. But as I said earlier, if we wanted to use the mass of a proton, it's so tiny, 1.7 times 10 to the minus 24 grams. So what we do is we define an atomic mass unit as equal to 1/12 the mass of a carbon-12 atom. I know it's a little bit of a convoluted definition, but the main thing to remember is that a proton equals 1 AMU and a neutron also equals 1 AMU. So if you have carbon-12, that means it has a mass of 12 AMU. If you had an atom that had twice the mass of a carbon atom, then it would have have a mass of 24 AMU. So mass is just a unit that we use instead of grams, because grams are so tiny, and so it's just a unit that we use. But you need to put it down if you're talking about mass number. You would use the unit AMU. All right. Now, where does that bottom number come in? That bottom number, as you can see, in some cases might exactly be 0.0, but in many cases is a decimal number. So you can see here boron 10.811, carbon 12.0107, etc. Where does that number come from? So far we've only used whole numbers. So number of protons is a whole number, and then the mass number, because it's a total of the protons plus the neutrons, is also a whole number. So where does this decimal come from? Well, it comes because remember we have different isotopes. Chlorine has 2 different isotopes. Carbon actually has 3 different isotopes. And then we average them together. So the bottom number is actually the average mass of an element if we take all the different isotopes and average them together. We call that the atomic weight or the atomic mass. Sometimes you'll hear atomic mass or atomic weight. It's going to be different from the mass number because it is an average. So the atomic weight is an average. It can also be expressed in AMU, and it is generally not a whole number, so that you can know the difference between atomic mass or atomic weight and the mass number, which is a whole number. All right, so let me tell you how we can find these atomic masses. They're not, well, let's go on. So remember, when we talk about an isotope, we are talking about a single atom. It's sort of hard to picture, but if we're talking about one particular isotope that has, say, 6 protons and 6 neutrons, we are talking about one single atom. However, when we look at the atomic weight of an atom, 6 protons and 6 neutrons is carbon. Let's look at carbon's atomic mass or atomic weight, and it's 12.011. So remember that that's a collection of atoms. Most elements have a mixture of several isotopes, and so the atomic weight is an average mass of the atoms. It's not just a regular old mass, though, and so this is where you have to be really careful. It's called a weighted average. A weighted average. Now, a weighted average has to do with how many of each type of element there are. Another way to look at it is a weighted average. You can say how many of each element do you have out of 100. So you're really taking an average out of 100 elements. So I'll give you an example in a minute, but let's just look at what I'm saying. So a practical way of determining an average mass of a group of isotopes is to say I have 100 atoms, and if I know what percent of each isotope there are of each type of atom, what I do is I can count how many out of those 100 are a certain weight and how many are another weight. So out of 100. Let's go on. I think you'll get it better if we do a particular example. So here's an example. Boron exists as two isotopes. There's boron 10 and boron 11. So let's just take a second. Boron 10, since boron has 5 protons, that means boron 10 has 5 protons and 5 neutrons. Boron 11 has 5 protons and 6 neutrons. Now, you might often, if you hear average and you think, okay, well, boron 10 and boron 11, if you take the average of those two, you get 10.5. Well, if you look now at the periodic table, you'll see that that is not what's shown. The atomic weight of boron is 10.81. So what's happening here? Well, it turns out that 20% of boron exists as boron 10 and 80% exists as boron 11. So another way to think of that, since you're talking about percentages, and you know what a percent is, if 20% is boron 10, that means like if you took 100 atoms, 20 of them would weigh 10. 80 of them would weigh 11. So right now, this is why the average is closer to 11 than it is to 10, because more of the boron atoms weigh 11 than they do 10. When you take a general average, like let's say if we took a classroom of people and we added their age together and divided by the number of students, that means that we're giving equal weight to every student. So if you take a normal average where you just add things up and divide by that number, you're assuming that they each have an equal weight. Well, in this case, boron 10 and boron 11 do not have an equal weight. As I just said, only 20 of them have a mass of 10 and 80 of them have a mass of 11. So one way that you can do it is you could take those 100 atoms and average them together, which is what we're going to be doing. So you could take a mass of 10 and add 20 of those together, and then take 11 and add 80 of those together, and then divide by 100. And that's where we get the average 10.81. A easy way to do it is to use this formula. It looks like a really scary formula, but it's really not. And actually, I'm not going to ask you to do a calculation like this. I just want you to understand the process. That symbol, that big sort of, is called a sigma. It's a big sort of looking E, capital E, stands for sum. And what that means is you add all of the parts together. The isotope percent means what is the weight of that, how much of that particular isotope are there, how many out of 100, say. And then the isotope mass is how much does that actual atom weigh. You add them all up, so you take the percent times the mass for each isotope that you have, you add them all up, and then you divide by 100. So I think the next slide will show us this worked out. All right, so for boron 12, we know that we have a percent, 20% weigh 10, so 20 times 10. 80% weigh 11. All right, so we add that up, we get 20 plus 880. And then if we divide that by 100, we get 10.8 AMU. If there's more than 2 isotopes, we add them all together. Before we go on, let me give you another example of a weighted average. Your grade in the class is actually a weighted average. The tests account for 60% of your grade, and the homework accounts for 20% of your grade. And it's sort of in that way, you know, if you mess up on the homework, hopefully you'll learn something and then you'll do better on the test. So if you think about your grade, if you got an F on a test or if you got an F on a homework assignment, which one's more likely going to affect your grade? Well, it's going to affect the test will affect your grade because the test has a higher weighted average. It weighs more. And so in this case with boron, because more of the boron weighs 11, then my average is going to be closer to 11 than it is to 10. And so this is mainly what I want you to get out of here. If you look at the atomic weight of an atom and I tell you what the different isotopes are, you should be able to tell me which one is the most abundant, or if there's more than if they're exactly equal. Let's look at the other example here. So there are 3 isotopes for carbon. Carbon 12 has 98.9%. Carbon 13 is 1.07%, and carbon 14 is 0.03%. Now, I do know that you all probably, when you hear percent, you divide by 100 or to get it back. Now, you don't have to do that. We're dividing by 100 at the end, at the bottom. So you can just use the percentages. If you want to divide by 100 each time, you can do that, or you can divide at the end. But anyway, since 98.9% of carbon weighs 12, and then we multiply that, and then 1.07 times 13, because only 1.07% weighs 13, and only 0.03% weighs 14. If you add that up and divide by 100, that's where you get the weight 12.01. So just looking at 12.01, if I said, here's my 3 isotopes of carbon, which is the most abundant, you would say, oh, well, the average is so close to 12, it must be 12. So that's, again, the main thing I want you to get out of it. Now, just like a mass number, atomic weights are also relative to the size of the atom. And so atomic weight, so if you look, for example, at the atomic weight of nitrogen, which is 14.0, and then you look at the atomic weight of silicon, which is 32 point, silicon is 28.1, what you would say is silicon weighs approximately twice as much as nitrogen does. And so you can have relative atomic weights. At first you might say, well, how is that true? Well, it's true because silicon has more protons and neutrons. Silicon has a atomic number of 14, so it has 14 protons, and it has approximately 14 neutrons, and so nitrogen only has 7 and 7, and so it's silicon is twice the weight. So that is the end of this first part of the lecture, and we'll finish up with I'll do another slideshow for the other part of this of Unit 3.